Good morning, everyone. So to start off with some announcements. So I posted the homework for this chapter online this morning. So that's going to be due not this Sunday, but the following Sunday. So chapter 12. A while to get through this chapter. And I also posted the conceptual questions. So good. So it's kind of reminding where we finished off yesterday. So we started talking about rotational kinetic energy. And we said was that any object which is rotating has the ability to do work. Hit that up there, but anyways, has the ability to do work because if I rotate this thing, I can use that rotational energy then to do work. Right? So that means I have to have the rotational kinetic energy. Now, rotational kinetic energy is defined as 1/2 I, which in this case is a pivot point, where I is what's known as the moment of inertia, times the angular velocity squared. So talked a little bit about this yesterday. So again, our replacement scheme says that x goes to theta, b goes to omega, a goes to alpha. These are all things we saw before. And now our new thing is that mass now goes to moment of inertia. Right? So this thing has identically the same structure as translational kinetic energy. So translational kinetic energy is 1/2 the mass times the velocity squared. So the rotational inertia, or the moment of inertia, which is the rotational analog of mass, is defined as the sum over the individual masses times the radius squared, or in terms of a continuous object, this is then the integral over the radius squared times dm. So notice here that r will be different as I choose different pivot points. So if I rotate this thing, for example, about this point versus this point versus this point, then the distance to that mass section now increases as I move away from it. Right? So r in this case is going to depend on the pivot point. So we want to understand a little bit better what this I is. What is this moment of inertia? And we're going to start off by talking about that is to talk about what is mass. Right? So what does mass physically mean? So not just how much of the stuff does this thing make up, but what exactly is mass? Right? So to answer that question, we can go back to Newton's second law. What Newton's second law says is that what? For a fixed amount of force, what happens to the acceleration if I increase the mass? So for example, if I put 10 newtons worth of force onto an object, what happens to its acceleration if I increase the mass? Goes down, good. So, sorry, give me 1 second here. Logistical things I have to take care of. Okay. Gallery, there we go. So, exactly. So the acceleration goes down as I increase the mass. So this, when we interpret mass then, is what's known as inertial mass, which basically is a measure of how resistant an object is to acceleration. The more massive it is, the harder it is for me to accelerate that object. Which means to get it to accelerate at a reasonable rate, I have to apply more and more and more and more amount of force. Right? So basically, our interpretation then of what mass is, what's known as inertial mass, which is different from gravitational mass, which we'll talk about later, is basically, again, a resistance, a measure of resistance, to acceleration. So this is what inertial mass, or what we just call mass, is. It's a measure of how resistant an object is to some type of acceleration. So what that means then is that this object moment of inertia, also known as rotational inertia, therefore is a measure of how resistant an object is to rotational acceleration, this angular acceleration. So what moment of inertia actually is this is a measure of how resistant an object is to rotational acceleration, or what we call angular acceleration. Now notice here, moment of inertia then has a higher or more complicated structure than simply mass. Mass, we quantify that by simply a number. What this thing says is that not only does the rotational inertia, or the moment of inertia, depend on the mass, but it also depends on how that mass is distributed. So as I change the distribution of the mass, I change the moment of inertia, which will then either increase or decrease the level of difficulty for me to rotate an object. Nate, come here. Come and see over there. So Nate will demonstrate that for us. In my panel. So I have this object. So this thing has mass on this side here, right? It has the rod itself. So the total moment of inertia in this case is the moment of inertia of the rod plus that of this extra part. Right? This is what this thing actually says. Total moment of inertia then is simply the sum over all the different objects. So the rod has a moment of inertia. This mass here has a moment of inertia. So the total moment of inertia is simply the sum of those two. So what Nate is going to demonstrate for us is first he's going to hold it here, and then go ahead and whip this guy around. And see how easy that is. Great. So now we're going to flip it around, do it on this side, and do the same thing. So which way was easier? The other way, right? And why is that? Good, that's right. So here, what's happening is my pivot point is down here. This mass is distributed here, so that means it's a very small r distance. So when I square a small distance, that becomes even smaller. But when I switch it to the other side, I now have a very large r, which means if I square a large r, that becomes even bigger, which makes it much more difficult for me to rotate. So even though I haven't changed the overall mass, the only thing I've changed is the mass distribution, which makes it harder to rotate. Another example is now these two. So same thing, I have a rod, two masses. In this case, they're very far away from, we're gonna do the pivot point, so you're gonna do that at the center. And then here we have them very close to the center. So hold one in one hand and one in the other hand. Yeah, try to flip around both of them. Okay, which one is easier? This one. Or again, exactly the same reason. Thank you, Nate. So in this case, again, this thing is easy to whip around because all the mass is concentrated very, very close to the pivot point. This one is now much more difficult for me to rotate around because the mass is farther distributed, which means I have a much greater R value, which makes this thing much more difficult to rotate. Same thing is true for this guy. So I took this trick, I wrote this thing about the center points. Endpoints. Now it's much more difficult for me to actually rotate this thing. Okay, why? I haven't changed the mass, but what I have changed is the mass distribution of this object. So for this guy, the center mass says all the mass is concentrated at the center. So if I hold it at the center, it's much easier for me to rotate, as well as I hold it on the side. Now that distance is much, much farther away from where I'm actually rotating this guy. So this is moment of inertia. So moment of inertia, again, is the analog equivalent of mass. It's a measure of how hard it is for me to rotate an object. But it only doesn't depend on the mass of the object. It depends, again, on how that mass is actually distributed. So the further and further I get away from where all the mass is, the harder it is for me to actually rotate this object. So this is moment of inertia. So the rotational energy then is going to depend on this moment of inertia, which is going to depend on where the pivot point is. As I change the pivot point, we'll change how hard it is to rotate, which will change the amount of energy that the thing actually has. Is okay with this? So how do I actually calculate a moment of inertia? So let's do that. So let's calculate some moment of inertia. So let's say I have a rod, one of these. This thing has a certain mass and it has a certain length. So here's my rod. This thing has a mass, let's call that capital M. Has a total length to it, let's call that L. So we want to know then is what is the moment of inertia of this object about two different pivot points. So for part A, we want to know what is the moment of inertia about the center of mass of this object. So if I was holding my rod here at the center, what's its moment of inertia? Part B then, I want to know what is the moment of inertia about one of the endpoints. This meaning that for part A, we're looking here. This is part A. Part B, we're going to choose one endpoint over here. So for both of these two, we want to know simply what is the moment of inertia. So how do we do this? What type of object is this? Is it a discrete object or a continuous object? Is it a point mass?
Oh, it's continuous.
It's a continuous object, right? So since this guy's a continuous object, this means that for part A, the moment of inertia about the center mass then is going to be equal to the integral of r squared dm. So good. So to do that, let's set up a coordinate system. Let's go ahead and say that I'm going to put my origin here at the center. This is going to be my coordinate system. So my moment of inertia then will be about the origin here, which is at the center of the mass. Good. So in this case, how are we going to do this? Well, first we're going to chop this thing up to a whole bunch of small DMs. I'm going to cut this little tiny section here and call this my DM. So that little guy then is my DM. So according to my coordinate system, the distance then from the origin to where DM is the distance r. So this is my distance r. So r then is the distance from the pivot point to wherever I slice my little tiny DM in this case. DM I'm just randomly choosing because I have to sum over all these DMs. But r here is literally the distance of x, so r is the same thing as x. R is simply equal to x. So I'm going to rewrite this then as being the integral x squared dm, and I want to integrate this over dm. Now, we talked about dm. dm can be one of three things, right? So dm is either going to be lambda dl, sigma dA, or rho dv, depending on the symmetry of my object. Now, if this is my rod, what type of symmetry does my rod have? So is this thing a line symmetry? Is it an area symmetry? Or is it a volume symmetry? It's a line symmetry, right? So in this case, since this thing has a line symmetry, we're going to rewrite that dm then is equal to lambda, where again, lambda is the mass per unit length, times dl. So dl then is simply the width of this little tiny section I cut out here. So this is dl. So if I draw down on here, all that means is if I cut out this little tiny section here, so this is my dm, then dl is literally just the width of this guy. That's what dl is. But since dl is along the x-axis, then this little tiny dl is actually the same thing as dx. In this case, dl is simply the same thing as dx. So I'm chopping out a small little tiny dx in this case. So what? So I'm going to rewrite this then as being the integral x squared lambda dx. So since I'm integrating over x, I'm going to integrate from one end of the rod to the other end of the rod, which means I'm integrating here from a negative L over 2 to over here to L over 2. Minus L over 2 to L over 2. Okay? Now, as long as this thing has uniform mass density, which we're going to pretend that it does, this thing is simply a constant, which means it comes outside of the interval. As long as we have this is constant, it becomes lambda integral minus L over 2 to L over 2 of x squared dx. What's the integral of x squared dx? Good, x cubed over 3. So this thing becomes lambda over 3 times x cubed, evaluated from minus L over 2 to L over 2. So let's put in our values of integration. Finally, what we get is that the moment of inertia about the center mass is equal to lambda divided by 3 times. So now I'm going to get an L over 2 cubed minus L over 2 cubed. So this is the same thing as lambda over 3 times L cubed over, what's 2 cubed? 8. Sure. If I have a minus and I cube it, is that a positive or a negative? That's a negative. So I get a minus, which becomes a plus, L cubed over 8. So this is the same thing then as what? 1/4. So this becomes lambda over 3 times L cubed over 4. Okay with that? So it's going to be the same thing then as 1/12 of the linear mass density times the length cubed. Well, remember, the linear mass density is simply the mass per unit length. So since this thing has a total mass of m and has a total length of L, that means that lambda is the same thing as simply m over L. It's mass per unit length. So if I plug that in, all that's going to happen is one of these L's are going to cancel. So it's becomes 1/12 the mass of the object times the length squared. So this is my moment of inertia about the center of mass. Right? Now, if I want to know the moment of inertia then about an endpoints, what do I have to do? Well, I have to redo the integral because I have changed my pivot point location. So in this case, if I was doing about the endpoints, I would have to redo this by putting my new origin here. So I call this the y-axis, this now the x-axis. Cut this thing into a bunch of small dm's here. So again, this is going to be dm, it's going to be lambda dx as before. This distance is going to be x. So everything stays the same, except now my bounds of integration aren't going to be from negative L over 2 to L over 2, but it's going to be from 0 to N. So let's do that one. So I do exactly the same thing here for part B. I get a moment of inertia about the end, then equal to, so the integral lambda times x squared times dx from 0 to N.
Wait, can you explain that last part? How do you see the end? How do you get it?
From here to here?
Yeah.
Oh, because lambda is the mass per unit length of the object. So if the object has a total mass of m and has a total length of L, then lambda is just that mass divided by that. Okay. So yeah, so when I put that in, that over L cancels out into those L cubes. Okay. Goes okay? Same things before. So if lambda is a constant, this becomes lambda integral 0 to L x squared dx. Integral of x squared dx, you guys already told me, is x cubed over 3. So this becomes lambda over 3 times x cubed evaluated from 0 to L, which is then equal to lambda over 3 times L cubed. Again, using lambda as m over L, this becomes 1/3 the mass times the length squared. So what is one of the problems then with a moment of inertia? Well, the problem is, as I change the pivot point, so if I was here pivoting about the center of mass at 50 centimeters, and I simply want to know what was the moment of inertia even 5 centimeters away, I would have to redo this integral every time. Which is fine, but it's not exactly convenient. Turns out there's actually another way we can do that. There's something which is called the parallel axis theorem. So let's talk about the parallel axis theorem. What's the parallel axis theorem? So the parallel axis theorem says is if I have an object, and let's say I know what the moment of inertia is about the center of mass. So let's say this is the center of mass. And I know what its moment of inertia is about this point. If I want to know what is the moment of inertia about any other point, let's say this point here, let's call that point P. As long as the rotation axis of P is parallel to that of the center of mass, there's a much easier way to actually find the moment of inertia about that point without having to redo this integral. So the moment of inertia, or the parallel axis theorem, says that if this distance between these 2 points is the distance d, then the moment of inertia about point P is simply equal to the moment of inertia about the center of mass plus the mass of the object times that distance squared. This is what's known as the parallel axis theorem. So the parallel axis theorem says that as long as we know the moment of inertia about the center of mass, I can then find the moment of inertia about any other point as long as that rotation axis is parallel. So it means if I took this thing and I rotate it like this, versus if I take this thing and I rotate it like this, I can find that moment of inertia without having to actually do this. So let's test it. So now we know the center of mass moment of inertia for this object. We know what it's about one of the points. Let's use this guy and actually come up with this guy without having to do this integral. Let's actually just do that. So let's use now the moment of inertia or the parallel axis theorem to then determine what is the moment of inertia about the endpoint. Let's see that this thing looks. Great. So let's say again, I want to know what is the moment of inertia about the endpoints. Well, according to the parallel axis theorem, this is then simply equal to the moment of inertia about the center of mass, which we now know, plus the mass of the object times that distance d squared. So what's that distance d squared in our case? Well, here we know this distance here, which means d is simply that distance, which is going to be L over 2. We're simply L over 2 distance away from that particular point. So it's going to be the moment of inertia of the center of mass plus the mass of the object times L divided by 2 squared. 1/2, or sorry, center of mass, moment of inertia, plus the mass of the object times L squared divided by 4. From here, we know the moment of inertia about the center mass is simply 1/12, so it's going to become equal to 1/12. The mass of the object times the length squared plus 1/4 the mass times the length squared. Mass times the length squared is the same thing, so this is going to be equal to the mass times the length squared times 1/12 plus 1/4. Well, what's 1/12 plus 1/4? Well, if I find a common denominator, this is the same thing as what? 3/12. So it's going to be 4/12. 4/12 is so this is the beauty of the parallax theorem. So the point of the parallax theorem is that as long as I know the moment of inertia about the center of mass of any object, I can find its moment of inertia about any other axis as long as that axis is parallel to its. The only thing I need to know then is what this is. The nice thing about that is somebody actually did all of these because they had a whole bunch of free time on their hands. Actually, it was just necessary. That's what they did. So there's a whole entire table in your book that has a whole bunch of moments of inertia about the center of mass already done out for you. Which means that if you want to know those moments of inertia about any other point, you go to that chart, which I think is table 12.1 or 12.2. You go there, you find the moment of inertia about the center of mass, use the parallax theorem, and then you're done. Like this. You don't actually have to do these integrals. Somebody else did them for you. Like this. Okay? What's up, Nate?
So what would be an example of it not in parallel? Like on like a diagram?
Oh, on like a diagram. So for example, if I wanted to rotate it about an axis this way. Okay. So what I mean by that is, let's say I wanted this thing, and let's say I know it like this, but I want to know how it rotated like this. Right? So that's a perpendicular axis. It turns out there's also a perpendicular axis theorem. We're not going to use that one in here because we're never going to do that, but it does exist. You will have to do that future in your engineering classes and things like that. But it's called the perpendicular axis theorem. So again, if I was doing something like this guy, so again, if I know how it rotates even about this point here, but I want to rotate it like this, that's a perpendicular axis. So as long as the rotation is still in this plane here, then this thing applies, fine. So yeah, whether it's here or up here or over here, as long as the axis is still somehow parallel to that, this thing works. But just not perpendicular. Okay? So this is how we actually calculate moments of inertia. Now again, for this class, we're almost never going to do these integrals. All we're ever going to use is this parallax theorem to move it to the point at which it is that we want it to be. That was okay? Now that we know how to calculate those, let's start talking about kinetic energy. Let's look at some examples of this guy. So now, let's consider this rotational kinetic energy in a problem. So this problem is going to be our Atwood machine that we looked at before, which has two masses attached to a string which goes over a pulley. Let's look at that thing. So here's my pulley. My pulley now is going to be massive. It's going to have a radius. And on this side, I'm going to attach one mass. Let's call this mass M1. On this side, I'm going to connect another mass. Let's call that mass M2. And let's give you some numbers. So let's say M1 here is equal to 35 kilograms. M2 here is equal to 38 kilograms. And let's say the mass of the pulley is 4.8 kilograms, and its radius is equal to 0.3 meters. So what's going to happen then is I'm going to take these masses, and allow this one to go down by a height of h, where h is equal to 2.5 meters. And what I want to know then simply is how fast are each one of these blocks moving by the time this thing goes down 2.5 meters. So by the time M2 reaches down here, I want to know how fast is this guy going in this direction. And by the time this guy reaches up here, I want to know how fast is this guy moving in this direction. We're going to do this two ways. So part A, we're going to do is we want to ignore the rotation of the pole. So in this case, we simply want to know how fast are those two objects moving by the time M2 has gone down 2.5 meters, M1 has gone up by 2.5 meters. I want to know how fast are they moving, ignoring the rotation of the pole. This is going back to what we did before. Part B then, we want to include the rotation of the pole. So we want to let this pulley actually rotate. In this case, again, we want to know simply what's the velocities. And then we want to compare those two velocities and talk about what's actually happening here, why this actually makes sense. So let's do that. Let's do part A first. So for part A, going way back to our last exam, we know that we're going to write the change in kinetic energy of mass 1 plus the change in kinetic energy of mass 2 plus the change in potential energy of mass 1 plus the change in potential energy of mass 2 must all be equal to 0 in this case because there is no work done by non-conservative force. Now, let's assume that again the initial velocity is equal to 0. So these guys start from rest and are going to move. So again, step 1, we're going to draw our picture. That's step 1. Step 2, we're going to label, which we already did. Our initial points, our initial points, and our final points. So here I'm going to go ahead and choose that this line down here is my y is equal to 0 location. Step number 3, what types of potential energies do I have in this case? Gravitational. So this is going to be the change of gravitational potential for each one of these guys. And step number 4, I already skipped until it's 0 because we have no work done by non-conservative force. Great. Step number 5, solve. So let's do that. So here, this is going to be equal to 1/2 m1 times v1 squared minus the initial, which is 0, plus 1/2 m2 v2 squared minus the initial, which is 0, plus, for this guy, m1, my final gravitational potential then is going to be m1gh minus the initial, which is 0. So again, it's m1 h minus 0 plus, for this guy, his final then is going to be 0 because he finishes down here, but his initial then is m2gh. So I'm going to get a plus 0 minus m2gh is all equal to 0. Now, what must be true about the velocity v1 to that of velocity v2? They're the same, right? So it has to be true is that m1 must be going upward as fast as m2 is going down. So since these two are the same, I'm going to go ahead and draw those two subscripts. Those two have to be the same. v1 must be equal to v2. So good. So from here, we want to solve for v. So these two will have v, so I'm going to factor out the v, move these two to this side. So we're going to get a 1/2 m1 plus m2 times v squared must be equal to g times h times m2 minus m. Finally, solve for the velocity. We get the velocity then is equal to the square root of 2gh m2 minus m1 all divided by m1 plus m2. So this is my velocity. Numbers, what I find in this case then is this is 1.42 meters per second. So that's how fast these two guys are moving. Good. So this is just a review of everything we did before. So now part B we want to do is actually take the rotation of the pulley into account. So what's going to happen now is that what? This mass will have to start moving up, so it's going to have kinetic energy. This mass is going to move down, so it's going to have kinetic energy. the pulley itself is going to start to rotate, and since it has mass, it has moment of inertia, and it's then going to rotate. So that thing also has kinetic energy. So let's write all that down. So for part B now, we now have the change in kinetic energy for mass 1, plus the change in kinetic energy for mass 2, plus the change in kinetic energy of the pulley, plus the change in gravitational potential energy of mass 1, plus the change in gravitational potential energy of mass 2, plus the change in gravitational potential energy of the pulley is now all equal to 0. So the only thing we've done is we've added in the pulley. This is the only little modification that we have done. So add that pulley. Here we're going to stick to the same picture. So if this thing starts from rest, this thing starts from rest, this one also starts from rest, which means the initial kinetic energy of this guy is also 0. Cool. So it's going to be equal to 1/2 m1 times v squared, because again, this thing has to be moving as fast as this one is, even if the pulley's there or not. Minus the initial plus 1/2 m2 times v squared minus the initial, plus my rotational kinetic energy, so it's going to be 1/2 the moment of inertia about the center of mass of this guy times its angular velocity squared minus the initial, plus my change in gravitational potential, so this stays the same, so this becomes m1gh times 0 plus 0 minus m2gh plus the pulley. Okay. So what happens with the gravitational potential energy change of the pulley? So this was my pulley. Okay. What's my pulley going to do? It's just going to rotate about its center of mass. Okay. So as this one moves up, this one moves down, this thing is just going to rotate like this. Which means that, did this thing have a change in gravitational potential energy? No, that's right, Ted. So in this case, the only way it's going to have a change in gravitational potential energy is if the center of mass location changes. Because again, center of mass says that I don't care about any of this mass distributed out here. All I care about is that this thing has a center of mass, which is located at its geometrical center. So as this thing rotates in a circle, the center of mass is not moving up or down, which means there is no change in gravitational potential energy of the pulley itself. That center of mass location stays exactly the same. So that means that its initial gravitational potential energy is equal to its final gravitational potential energy, which means the change is simply equal to 0. So this guy is constantly equal to 0. Okay? Now, the next thing is the angular velocity of the pulley independent of the linear velocity at which these two guys are moving? Meaning, is this guy shooting up with a velocity v, this guy's shooting down with a velocity of v, and this guy's just rotating with an omega that is whatever? No, omega is dependent on how fast these guys are actually moving. So how is it dependent on how fast these guys are moving? Well, what must be true is that I was looking at this point on the pulley, or this point on the pulley. What has to be true then is that the linear velocity or the tangential velocity on the side of the pulley here, and this translational or tangential or linear velocity on this side of the pulley must match exactly how fast these guys are going. Because this guy is moving up because the cord is being pulled up, so the cord must be being pulled up as fast as this thing is rotating at that moment. So what has to be true then is that the tangential velocity on the exterior of the pulley here, this point, must be rotating upward at exactly the same rate at which the mass is moving upward. So it means as far as the pulley is concerned, his tangential velocity on this side and this side must be that of the velocity of the blocks. Okay with this? But we know that the tangential velocity is related to the angular velocity by simply the radius of the pulley. Which means that the angular velocity that the pulley has must then be equal to the tangential velocity divided by the radius. Everyone okay with this? Good, let's put that back in. So this becomes 1/2 m1v squared plus 1/2 m2v squared plus 1/2 the moment of inertia about the center of mass times the velocity squared divided by the radius squared plus m1gh minus m2gh plus all n be equal to 0. Okay? This v is the same as this v, which is the same as this v, so I can factor all that out. So this finally becomes 1/2 the mass of the first plus the mass of the second plus the center of mass, moment of inertia of the pulley divided by the radius squared. All times the velocity, then squared, must be equal to m2 minus m1, all times gh. Okay? Solve this finally for the velocity. Velocity then is going to be equal to the square root of 2gh m2 minus m1, all divided by m1 plus m2 plus moment of inertia about the center of mass divided by the radius squared. Now for our problem here, we're treating this guy as a solid cylinder. And it turns out that the moment of inertia about the center of mass of a solid cylinder is simply equal to 1/2 the mass of the object times its radius squared. So this I just found from table 1. Plug that into here. This thing finally then becomes the square root of 2gh m2 minus m1, all divided by m1 plus m2 plus 1/2 the mass of the pulley. Radius cancel out. Plug in my numbers. What I find in this case then is this is moving now at 1.4 meters per second. So slightly slower than what it was moving before. So, is this surprising that it's moving slower? So would you have thought it would be moving slower, faster, or the same as before? So does it make sense that this thing is actually moving slower? So is this a surprising result that it's going slower? So let me ask you a different one. Why does it make sense that it's going slower? So why would it make sense that this guy's actually moving slower? Well, let's think about this in a mathematical way. If I compare this guy to this guy, what we notice is that now there are 3 kinetic energy terms here as opposed to here, which there are only 2. So what's happening in this problem is that what? The energy going to the kinetic energy comes from the change in gravitational potential energy. As I change the gravitational potential energy of this, the energy then gets diverted into 2 different types of kinetic energy. In this case, the kinetic energy of him and the kinetic energy of him. But if I now say, well, the pulley now is going to start to rotate. As the pulley then starts to rotate, what do I have to do? Well, I have to take that same amount of gravitational potential energy, but now divert it into this kinetic energy going up, this kinetic energy going down, and the extra kinetic energy I need to rotate this object. So what happens then is I have to sacrifice energy into causing this thing to rotate, which then makes these other objects have to move slower because I have to divert the energy now into 3 avenues as opposed to just 2. Because I have a fixed amount of change in gravitational potential energy. This is fixed. So it makes sense that these are going slower because I have now more objects I have to rotate, which means I have to divert more energy, which means I have less energy per object to get each one to move. So this is what's actually physically happening. So as this thing actually rotates, it takes energy to rotate it, which means I have to take the energy from someplace else. I can't create energy to make it move as fast as it did before. So as long as our pulley then has mass to it, I have to get that thing to rotate. It takes energy to do that. So when I start doing it, these things have to move slower than what they did before. Okay? So next time we're going to talk about is what happens if I take an object and I roll it. What happens then to my kinetic energy in this case? In this case, we're going to look at what's known as rolling without slipping. In this case, I want to take an object and I want to roll it, which means that this thing is going to have a center of mass velocity and it's going to have an angular velocity. So this thing's going to be doing this. So in this case, I'm simply going to take this guy, watch your toes, and do that. A little bit there. That's better. So in that case, I just want to roll this guy. Right? So what I want to know in this case then is what happens to the total kinetic energy of this object? What is my total kinetic energy for this particular object? So good. So first thing, notice that this thing rolling, right, when I roll this thing across the table, is equivalent to this thing moving in this direction at a center of mass velocity, and this thing rotating about its center axis. So basically, this thing doing that is equivalent to this thing just moving in this direction with a center of mass velocity v center of mass. Plus, this thing just rotating with an angular velocity about its center of mass. Okay with this? Now, since it's rotating, what that means then is that this thing has a tangential velocity, which is the center of mass velocity in this direction, tangential center of mass velocity in this direction, and then here my center of mass is 0. It's not moving at all. So if I superimpose these guys on top of each other, what's happening? So what this is saying is that my wheel, which is doing this, then has this velocity plus this velocity, which means on the top portion here, this thing actually has a velocity which is twice the center of mass velocity of the object. Superimpose this guy on top of this guy simply has a center of mass velocity in this direction. But this one is opposite the direction of this one, which means that this point here is actually stationary. There is no velocity at this point. Which means that what's actually physically happening is this is becoming the pivot point of my rotation. So as my wheel is doing this, as far as the wheel is concerned, the wheel is actually doing this. This is my pivot point. My wheel is then rotating about this pivot point, where this has a center of mass velocity. Up here has twice the center of mass velocity because it's twice the distance away. So this motion here, there we go, as far as the wheel is concerned, is the wheel is simply doing this. This point stays fixed, and this is actually rotating about my finger. Okay with this? Which means that the rotational kinetic energy is simply the rotational kinetic energy about my pivot point down here. This is the total kinetic energy. Now, let's see what happens with this thing a little bit further. So this end is equal to 1/2 the moment of inertia about that pivot point plus, times the angular velocity squared at which this guy is moving. This is my total kinetic energy. But we can rewrite the moment of inertia about this point in terms of this point by using our parallel axis theorem. So let's go ahead and do that. So it's going to be the same thing then as 1/2 the center of mass moment of inertia plus the mass of the object times the distance squared. Well, what's the distance between this point and this point? The radius, right? So it's going to be equal to the radius squared times the angular velocity squared. So let's separate this. So this becomes then equal to 1/2 the moment of inertia about the center of mass times the angular velocity squared plus 1/2 the mass of the object times the radius squared times the angular velocity squared. But again, I know the angular velocity squared is simply related to the center of mass velocity by the radius. Same thing we just looked at. So we know that omega is equal to the center of mass velocity divided by the radius, which means this thing becomes 1/2 the inertia about the center of mass times the angular velocity squared plus 1/2 the mass of the object times the linear center of mass velocity squared. That radius squared is going to cancel out this radius squared. Okay. Well, this thing is simply the rotational kinetic energy about the center of mass. And this thing is simply equal to the translational kinetic energy of the center of mass. So when I have an object which is doing this, rolling without slipping, the total kinetic energy of this object is simply equal to the kinetic energy that this thing has moving in a straight line of its center of mass, plus the kinetic energy this thing has while it's rotating about the center of mass. This is then the total kinetic energy. So the total kinetic energy for an object rolling without slipping simply is the sum of these two kinetic energies. How fast it's rotating about the center of mass, and how fast is that center of mass moving. That's it.
What is that second thing called?
This one, this is the translational kinetic energy of the center of mass. Okay with us? So this motion here, again, oops, can't see the roll straight today. There we go. That motion is simply this motion plus this motion. That's it. So the total kinetic energy is simply the kinetic energy of this plus the kinetic energy of this. That's it. Good. So let's do a quick example of this. I'll try not to take out anybody's toes. So here, what I want to do is take these two masses. These two have roughly the same amount of mass. They have pretty much exactly the same amount of radius. And what I want to do is I want to race them down this ramp. And what I want to know is which one of these two is going to win at the end of the day. Is it going to be this one? Or is it going to be this one? Now, if I didn't take rotation into account, which one would win? They would tie. Right? So if I didn't have any rotation into account, they're going to go down exactly the same heights. What we know is that they have the same linear velocity at the bottom because they go down by exactly the same heights. But now that I'm going to take rotation into account, using specifically this rotation, which one of these two guys are going to win? And there's something else I want to point out in this case. Woodwind's going to win? So how many want to go with Teddy and say that Woodwind's going to win? So by default, the rest of you are on this one, or how many of you say this one? Nate's the sole one. There we go, Ruth. Got back up. How many have zero idea? There we go. Let's find those, and then we'll talk about why that is. So, Ethan, watch your toes. So I'm going to simply hold these guys here. I'm going to let them go, and Ethan's going to tell us which one actually. Which one got to your foot first? The wood one. Right? Why is that? Why is that? We're going to mathematically do this as well, but let's talk about it first. Why does it make sense that this one actually makes it to the bottom first before this one does? So what's true about this one's mass distribution versus this one's mass distribution?
There's a better center of mass.
That's right. So most of the mass on this one is concentrated more towards the center because it has uniform mass distribution all the way through, where this one has a mass which is distributed much further away. What does that do to the moment of inertia? Which one has the smaller moment of inertia? This one, right? Which means that, again, if our moment of inertia is simply how resistant it is for an object to start to rotate, which one is easier to rotate? This one. Okay? Which means it makes sense that this one's going to be moving faster than this one because this one is more reluctant to start to rotate. So as it's more reluctant to start to rotate, it takes more energy for me to actually to rotate it, as opposed to this one because it's easier to rotate. So if this one is easier to rotate, it takes less energy for me to actually rotate this thing, which means it can have more translational velocity at the end, because if I put less here, I can put more here. Right? Does this make sense? Where this one is more resistant to rotate, which means I have to put more energy into the rotation, which takes away from the translational energy, which means it can't be moving as fast at the end of the day. Now, we'll actually do the math on this on Monday. I was hoping to get through this today, but apparently I was talking too much. It happens. Now, the other thing is, when we actually write this thing down and we do our conservation of energy, my first question then is there a work done by a non-conservative force in this case? Meaning that when I put these guys on here and I let them go and I let them slide, I that we did. Is there a work done by non-conservative force? Meaning, what causes these guys to rotate?
Gravity.
Not gravity.
Friction.
Friction. Good. Gravity helps, but it's not. Gravity is actually friction. What type of friction? Is it a kinetic friction or is it a static friction? It's a static friction, right? So in this case, what's happening then is even though there is a friction force present to cause these guys to rotate, that friction force is not a non-conservative force. The reason for that is because if I wax this thing, what would happen to the friction force? It would be zero. Meaning if I waxed it and I let these guys go, would they rotate at all? No, they would just slide down, which means it would be all translational kinetic energy, so they would hit the bottom at exactly the same time. Which means that the only thing that the static friction is doing in this case is to cause them to rotate. Okay? So in this case, what it's doing, the static friction is not a non-conservative force, it's simply causing this energy to go into this energy. This is the catalyst. Okay? Now, it would be a non-conservative force if these guys were actually doing this. Sliding mostly and slowly rotating. In that case, it would be what kind of friction? Be a kinetic friction, which in that case, it would be a non-conservative force. But as long as these guys are simply doing that, it's a static friction, which only causes it to rotate, which causes it to divert energy from one type of energy to another energy. So in that case, there is no non-conservative force, which means when we write down our conservation of energy, when we analyze this problem, the right-hand side will simply be equal to 0, even though there is a static friction present. But again, that static friction's purpose is only to divert energy from one form to another. So we'll start out with this on Monday. And where's my stop button?